Have you ever been outside at night and you look down a straight road to notice that a motorcycle is coming down the road? But, oddly enough, as this motorcycle approaches towards you, you notice that it isn't actually a motorcycle, but that it's a car? As the single light, which you thought was a motorcycle, approaches, the single light separates into two lights, which become clearer as they get closer and closer. This phenomenon, which I just explained, and which I'm sure you have noticed in your life, can be explained by the Rayleigh Criterion. The Rayleigh Criterion specifies the minimum separation between two light sources that may be resolved into distinct objects. Now, to understand the Rayleigh criteria, you first have to understand what is resolution. Resolution is the process or capability of making distinguishable the individual part of an object, closely adjacent optical images, or sources of light. To make this simple, resolution is the minimum distance required between two objects to discern between them as individual objects. These two dots here are well resolved. That means that you can see each one distinctly and individually. Here, these two dots are just resolved, meaning that upon immediate evaluation, it might be difficult to tell if it's one or two, but by looking closely, you can decipher that it is two distinct objects. And lastly, unresolved objects. This one is where the two dots are undecipherable, and they look like one large object altogether. Now, to understand resolution, we should look at a couple objects that use them. The first one being a microscope, which look at very small objects, binoculars, which are used to look at objects that are at a distance away, such as birds or wildlife, telescopes, which are used to look at objects that are even further away, such as stars or other planets. Because of this, a telescope will need to have better resolution than a pair of binoculars. And lastly, cameras, which are used to capture images. If you've ever taken your phone out quickly to take a picture but failed to let it focus, you'll notice that the image has a really poor resolution. You're not able to really understand what the picture is. All of these objects use resolution to allow the viewer to see a clear image. If these are out of focus or have poor resolution, then the observer is unable to decipher what the image is. Now, what do all these have in common? Light. They all take in light. And to understand resolution and Rayleigh's criteria, we have to understand the characteristics of light. Now, we know that light acts both as a particle and wave. However, the first characteristic you really need to know is how waves interact. Waves either interact constructively or destructively. When waves collide with one another, they interact in one of these ways. The first one being constructive. If we look here, these two waves are equal. They have the same frequency, they have the same wavelength, and the troughs and the peaks line up, as you notice here. Now, what happens if these two waves collide is constructive interference, and the wave will grow. They will add to each other. Now, destructive interference. This is opposite of constructive, and what happens is when there's two different waves that don't align, and you can notice here that this trough lines up with this peak, you're going to get destructive interference. And you can see here that the output wave is actually smaller than one of the input waves. To understand this, I like to think of addition. When you have two positive numbers, you're always going to get a number that's bigger than the two positive numbers. But if you add a positive and a negative number, you're going to get something that's in between the two. It's never going to be above the largest, and it's never going to be below the smallest. Now, the next and perhaps the most important characteristic of light to understand is how light is able to diffract. If we look at this image here, we're going to say that this red dot is a light source. And these white lines here, they're going to represent barriers. And this right here is going to represent a hole within this barrier. Now, if light is emitted from this dot, it's going to travel towards this hole. And as light hits the hole and enters the new space, the light wave is going to diffract. This occurs because the wave is looking to spread out into the existing area. Diffraction means that the light bends. If the wavelength is equal to or smaller than the size of the opening, we get what's called true diffraction. Now that diffraction is going to spread out into this area. That diffraction is just an extension of the wave. And what happens is when it hits the back screen, it creates a certain type of pattern. We'll call this a diffraction pattern. Now I'm going to get rid of the other waves so we can focus on the diffraction pattern. But the diffraction pattern shows the intensity of light in specific locations across the screen. As we see here, the higher peak at this location shows a greater intensity. And there's a peak here, but it's a lower intensity. And then another peak here, which is even less. And now notice that as we move the dot, the diffraction pattern also shifts and changes. And if we add a second light, we're going to see a diffraction pattern of the second light, which is very similar to the diffraction of the first. Notice on these how and where there's going to be constructive or destructive interference between these two patterns. Now, we discussed resolution types, and if we look at the 2 points with the highest intensities, which are called the central maximums, we see that they aren't overlapping very much. There's a little bit of overlap in here, however, they each have this large peak at the central maximum. There may be some small intensities, but we don't really need to worry about that when discussing resolution. Now this right here is going to be what's called well resolved, like we talked about. And if we were to look at it from the top, this is what we're going to see. This is going to be the top of the central maxima and the top of the other central maxima. Now, technically, they're going to have a target-like appearance where they're going to be surrounded by other rings that are going to be dimmer. And this occurs because of these out here. There still is light and some intensity, however, it is not as bright. So now let's look at what happens if we move the lights a little bit closer together. Say we put the light sources at the exact same position. Their patterns are going to overlap perfectly, as long as the light intensities and wavelengths are equal. Now how about if the lights aren't in the exact same position, but they're extremely close? Now we see the central maximums are overlapping and they're not going to be resolved. If we look from the top, like we did before, we see that there is overlapping. And the only way we can decipher there's two objects here is because of the color. Now if we make this white, we see, there it is, unresolved. Now coming back to Rayleigh's criterion and how it explains this, as two objects become closer, they become harder to decipher between. And as they become apart, further apart, they become easier to decipher between. Now, another example that I want to show you. If you look at this, you can see 5 bars. You're able to distinguish each one. Their distance becomes smaller between the next as you go from left to right. If you notice these two at the end, they are extremely close, but you're still able to decipher that there are 2 lines. I want you to stand up and walk to the back of the room, turn around and look at the lines. How many do you see now? Now you're going to see 4 lines. These end to appear to be 1. And this is occurring because of the principles we've just talked about with resolution. Now, if you were to keep walking back further and further away, eventually these lines would stack up so that you'd have 3 and then 2 and then 1, the further you got. Now, we were talking about how the distance between the two is affecting, but now as you get further away, it's affecting. Something that's important to understand is it's not actually the distance, but it's the angle that's formed between the two objects and the observer. Here is Rayleigh's criterion. Rayleigh's criterion is a formula, and it really shows us how we're able to decipher or discern the minimum angle, the angle we were just talking about. Now, this equation says that the sine of the minimum angle needed to discern between two objects is equal to 1.22, which is a constant, and we can refer this to as Rayleigh's constant, multiplied by the wavelength of the light being viewed divided by the diameter of the hole in which the light is passing. And so I want to walk through this math and how it works. Say we have two objects that are 100 meters away. The wavelength is 500 nanometers. We'll say the light is passing through a 4 millimeter pupil. That is the smallest distance, what is the smallest distance that we can decipher between these two objects? Now we'll put the 500 nanometers in as a wavelength, 4 millimeters in as the pupil diameter. We can solve for that to get about 1.525 e to the -4th radians. That's our angle, this angle that we see right here. Now what we can do is we can set the tangent of that equal to opposite over adjacent. The reason we can set a tangent is because the tangent and sine at such small distances are going to be nearly equal. Now we know it's 100 meters away. 100 times the tangent of our angle is equal to the opposite. That opposite is equal to 0.015 meters. And we're going to multiply that by 2 because we have twice that distance, which gives us roughly 30 millimeters. Now, coming back to the observer, we talked about the pupil. Let's talk about how the eye works. And if we turn the eye here, we can see this is the pupil, this is the iris, which is a muscle. We have this right here, which is the lens, which helps light focus. And these little black lines here are little muscles that help with focusing that lens. This is a very simple image of the eye, but it will help you understand what's happening. Now, as the light passes through the pupil, we get a diffraction pattern. And that diffraction pattern hits the back of the eye, which is known as the retina. The retina has a bunch of little cells in it, consistent of rods and cones. Rods pick up black and white light, while cones pick up colored light. Now, if we go back to the front of the eye, how do we know the distance of the diameter of the pupil? Now, something that's interesting is the diameter will actually change. The iris is a big muscle, and what happens is it will expand, dilate, or contract, become smaller. Now, this occurs when there's excess light or lack of light. So at night, your pupil is going to get bigger to let more light in. And during the day, your pupil is going to get smaller because there's excess light, so it's going to want to let less light in. Now, if we go back to that original thing that we talked about, the car, the motorcycle, what is this object? We can see here that the observer can only see one object. It's one light. And you can see that there's two lines here that represent the pathway those light is going to take. And we're going to see now this angle between these two lights has increased past the minimum angle. So he can now decide and say, it's a car. As it gets closer, it continues to expand past that minimum angle until it arrives at him, and he knows it's a car, not a motorcycle. Thanks for watching.